Welcome students. In this lecture, we are going to see how to form a partial differential equation by eliminating functions. I think you remember what we had done in the last class. We had learned how to form a PDE by eliminating arbitrary constants in the previous class. Today, the same we are going to do, but by eliminating functions. And this is the procedure of this method. In the first case, when an equation involving arbitrary functions like f, g, 5, etc. is given, we differentiate the equation partially with respect to x and the next with respect to y. And from all these equations, whatever we get, we will try to eliminate the functions involved in that. Another case we have when we have a particular form of equation as f of u comma v equal to 0. In that case, there is a formula directly given for the PDE, that is determinant dou u by dou x, dou v by dou x in the first row, dou u by dou y and dou v by dou y in the second row equal to 0. Now let us solve some problems in this method. First one, look at this problem. Obtain partial differential equation by eliminating the arbitrary function from z equal to f of x squared plus y squared. So first consider the function equation z equal to f of x squared plus y squared. So as usual, to form PDE, what we do? We need to differentiate partially with respect to x, and then we will move on to differentiating partially with respect to y. So the same process we are going to do here also. First, when we differentiate this given equation with respect to x partially, we get left side we have z, so that when we differentiate, we get dou z by dou x, which is actually p, which is equal to f of x squared plus y squared. When you look at this term, what does it say? It is a function of x squared plus y squared. So basically, it's f, which is a function of x squared plus y squared. Like it may be cos of x squared plus y squared plus x squared plus y squared the whole cube, like that. So everything will be in terms of x squared plus y squared. That is the meaning. So when we differentiate, first we need to differentiate the f. So that f, when we differentiate, it becomes f dash into inside. It's a function of x squared plus y squared, right? So inside what we have? X squared plus y squared. So that when we differentiate with respect to x, we get into 2x. From here, you can get the value of f dash as p by 2x and mark this equation as 1. Now same process continue, but with respect to y, that is differentiating partially with respect to y. What we get? Dou z by dou y equal to, actually that is q, equal to, first when I differentiate f, we get f dash into y squared. When I differentiate, we get 2y. So from here, we have f dash equal to q by 2y. If you mark this as equation 2, now observe the equations 1 and 2. What do you get? Yeah, both are the values of f dash. So we can equate these two. When we equate these two, we get p by 2x is equal to q by 2y. Look at this now. Do we have any function involved? No. So we have achieved what we have. What is our aim? We need to remove the function. So here there is no function. Also, we have inserted the partial derivatives, because our ultimate goal is to create a partial differential equation. So obviously partial derivatives also has got inserted. So this is the required PD. That is, just when you simplify, you get py equal to qx. Moving on to the next problem. Look at this. Form partial differential equation by eliminating the function f from z equal to f of xy. So here the equation is z equal to f of xy. So as usual, differentiate partially with respect to x first. We get dou z by dou x, which is p, equal to f. When we differentiate, we get f dash into, now we have to differentiate that x into y. So with respect to x we are doing now, so with respect to x when we do, y is going to be constant. So it's like, just imagine x into y as 2x. So usually 2x when we differentiate, what we get? Into 2. So the same way, x into y when we differentiate, it's going to be y, because y is now playing a constant role. So from here we can get the value of f dash as p by y. Next, similarly proceeding, differentiating partial with respect to y, we get dou z by dou y as f dash into, with respect to y when we do, x is going to be the constant. So it is f dash into x. From this equation, we will again have a value for f dash as q by x. Now look at these two equations 1 and 2. Both give the value for f dash. So we can equate them. P by y is going to be q by x. Now when we look at this equation, all the functions have got removed. Of course, we have only one function in this problem. So the function has got removed and partial derivatives has come in. So it is a partial differential equation. Let us move on to the next problem. Find the PDE by eliminating the function phi from phi of z squared minus xy, comma xyz equal to 0. Now look at this equation. This is not the usual form. We have a specific form here, phi of u comma v equal to 0. So do you remember in the procedure we had said there is a special case f of u comma v equal to 0. So this comes under that particular case, where u is z squared minus xy, comma second coordinate v is x by z. So for this particular case, there was a formula directly given for the PDE. Do you remember? Yeah, this is the formula, determinant dou u by dou x, dou v by dou x on the first row, dou u by dou y, dou v by dou y on the second row equal to 0. So just we need to finish this determinant. So let us do that. The first row, first column, dou u by dou x. So look at u here and differentiate that with respect to x. What we get? 2z into dou z by dou x, that is p, minus x into y. It is like product form. So when we differentiate with respect to x, y is going to be constant. So minus y. Now on the same first column, second row, let us complete the first column. So now dou u by dou y we need. What is dou u by dou y? 2z into dou z by dou y, which is q, minus x into y when we differentiate. With respect to y we are doing now. So x is going to be a constant. So minus x. Now let us move on to the second column. Dou v by dou x on the first row. But what is v here? X by z. It is of u by v form. I think you all remember how to differentiate u by v form. Otherwise, again I'll repeat. Whenever you have u by v, when we differentiate that, denominator is going to be v squared. So here we have z squared. On the numerator, what we need to do? Keeping the denominator, first you differentiate the numerator. So keeping z, when I differentiate x, I get 1. So z minus, keeping the numerator x, now differentiate the denominator. Z when I differentiate, I get dou z by dou x, that is p. So that's what we have here, z minus px. Now moving on to dou v by dou y. Now with respect to y when we do, look at this v. Here we have x by z. With respect to y when we do, x is going to be a constant. So it's just like 1 by z, differentiating 1 by z. When we differentiate 1 by z, what we get? Minus 1 by z squared. So that is why we get minus 1 by z squared. Of course, x is sitting as a constant into dou z by dou y, which is q. So that is why here we have minus x x by z squared into q equal to 0. Just what we need to do here is taking the determinant and simplifying, you will reach to this solution, which is the required PDE, and of course there is no function involved in the final answer. Let us move on to another problem. Obtain the PDE by eliminating the functions f and g from this given equation. Now consider the given equation. What is the difference you observe in this problem compared to the previous ones we have finished? The two functions f and g. So far we were doing problems having just one function. So at this point I wish to give you a clue. When we have problems having just one function, we will be able to eliminate that function with the help of just the first order derivatives p and q. But when we have problems like this having two different functions, we may have to calculate even the second order derivatives in order to eliminate these functions. So this is a clue which you have to remember. Now let us start partially differentiating with respect to x, the given equation. What we have? P, which is dou z by dou x, equal to the first function is f, that when we differentiate f dash, of course, into that x plus it with respect to x when we differentiate, we get 1, plus g when we differentiate g dash, into that x minus it when we differentiate with respect to x, we get 1. Now let us differentiate this equation again with respect to x. Then we get the second order partial derivative dou squared z by dou x squared, which is equal to, now the first term is f dash, that when we differentiate we get f double dash, of course, into x plus it when we differentiate 1, plus g dash when we differentiate we get g double dash, again that x minus it when we differentiate with respect to x we get 1. So mark this equation as 2. Now let us differentiate the given equation with respect to t. If you observe here, we don't have x and y, but instead we have x and t. So here q is going to be dou z by dou t. Okay. The first term f when we differentiate f dash into that x plus it with respect to t when we differentiate we get I, plus g when we differentiate we get g dash, and that x minus it when we differentiate with respect to t we get minus I. Call this equation as 3. Now once more let us differentiate because we need till second derivatives. So once more differentiating this equation with respect to t, we get dou squared z by dou t square. The notation let us call as a script t because we need to differentiate between the variable t and the partial derivative. So that's why I have used a different script t here, which is equal to, the first term is I into f dash. So when we differentiate, what we get? F dash when we differentiate, f double dash into that x plus it when we differentiate, we will get I. So already one I was there. So now we will get I squared. Similarly, plus g dash of x minus it when we differentiate, we get g double dash into minus I, again we will get. Now already minus I was there, so one more minus I when we get, totally we will have I squared. Now look at this equation. Is I squared not common? So we can write this as I squared into f double dash plus g double dash. But when you observe from equation 2, that f double dash plus g double dash is going to be just r. So we have t equal to I squared r, or t equal to minus r. So the equation becomes r plus t equal to 0. That is dou squared z by dou x squared plus dou squared z by dou t squared equal to 0. So which is the required partial differential equation, since we have eliminated both the functions f and g and we have only partial derivatives involved. Let us do one more problem with the equation having two functions. So consider this problem. The given equation is z equal to x squared f of y plus y squared g of x. So as I said earlier, we need till second order partial derivatives to eliminate two functions. So let us first find all the partial derivatives with respect to x. When we differentiate partially, we get dou z by dou x as x squared. When we differentiate, we get 2x into f of y is going to be constant, plus second term we have y squared, which is a constant, into g of x. When we differentiate, we get g dash of x. Mark this equation as 1. Next, differentiating this again with respect to x, we go to second partial order derivative, second order partial derivative, that is dou squared z by dou x squared, which is equal to 2 into f of y is going to be constant because we are doing with respect to x, and that x when we differentiate we get 1, plus second term y squared is constant into g dash of x. When we differentiate we get g double dash of x. Now we'll move on to differentiating with respect to y. So q, which is dou z by dou y, is going to be first term we have x squared into that f of y. When we differentiate we get f dash of y, plus y squared. When we differentiate we get 2y into g of x is going to be constant. Next, t, which is dou squared z by dou y squared, is going to be differentiating this again with respect to y. So we have x squared constant function into f dash of y. When we differentiate we get f double dash of y, plus 2 into y. When we differentiate 1 into g of x is going to be constant. Next, the mixed partial derivative, that is dou squared z by dou x dou y, also we need for this problem, which is going to be either you can do this as differentiating dou z by dou x with respect to y, or differentiating dou z by dou y with respect to x. So anyway, let us look at the first partial derivative p, which is dou z by dou x. That when you differentiate with respect to y, we get 2x into that f of y. When we differentiate we get f dash of y, plus y squared. When we differentiate we get 2y into g dash of x is going to be constant. So call this equation as 5. Now our next work is to eliminate these functions f, g, f dash, etc. using the equations from 1 to 5. With few algebraic skills we will be able to do that. So from equation 1 we have y squared g dash of x equal to p minus 2x f of y, and hence y g dash of x is p by y, just dividing y to the on the either side, p by y minus 2x f of y by y. Similarly, from equation 3 we will have the value of x squared f dash, and hence the value of x f dash, and call this as equation 7. Why we are finding these two values specifically, that is y g dash and x f dash? Because from equation 5 we have s is 2x f dash plus 2y g dash. So that is why we are finding these values. Now let us substitute from equation 6 and 7 the values of y into g dash and x into f dash in s. So when we do that, and doing some more little bit simplifications, you can get these equations which you can observe. Of course, taking that minus 4 term, common term between the second and the fourth one, and now take LCM in the last term. And when you take LCM in the last term, you can observe it is minus 4 by xy into y squared g of x plus x squared f of y, which I have highlighted in red. Can you observe what is it? Yeah, if you look at the question, we will get this is nothing but the value of z. Now look at this equation. I think we have removed all the functions. There is no function f, g or f dash anything in this, and we have got the partial derivatives also. So this is the required partial differential equation. So I think you would have understood the process of eliminating the functions to form the PDE. So using whatever you have learned, try these two problems. It will take around 20 minutes to half an hour. So students, in today's lecture, we have learned how to form a partial differential equation, especially by eliminating functions. And in the next lecture, we'll be seeing how to solve a partial differential equation, specifically the first order PDE and of type 1. Thank you.